Next, we'll use these concepts of hypothesis testing to discuss what is called confidence region and significance of parameter estimates. Let's take the null hypothesis H0 that theta is 0 and the alternate hypothesis H1 prime theta is greater than 0. So again, this is now not a simple hypothesis. And we are going to test based on a set of observations, Zi, and such observations. And the model for these observations is each Zi is the theta, which might be 0 positive, plus a Wi. And the Wi are noises. They are independent, identically distributed IID, Wi, or Gaussian zero mean variance sigma square. So what we have is H1 prime, a composite hypothesis defined by more than a point, an interval, a semi-infinite interval in this case. And the test is subject to PE1 is alpha, namely the force alarm, the type 1 error probability should be alpha. What is the likelihood ratio of our hypothesis H1 versus H0? Lambda of H1 prime and H0 is the PDF of Z given theta divided by the PDF of Z given theta equals 0. So again, with a little bit of cancellations, we end up with the exponential of constant times the sum Zi squared minus Zi minus theta square, open parenthesis, cancel, and end up with a function of the sum of Zi's. So the comparison of the above to a threshold is equivalent to comparing the sample mean of the observations to another threshold, 1 over n sum Zi. You can see here this, it's convenient to use division by n, so the numbers are more or less of the same order of magnitude. Once this is evaluated, the Z bar, then its comparison to a threshold to be determined, lambda 1, will yield acceptance of H1 prime if this Z bar, the average, exceeds lambda 1. If it's below lambda 1, we'll accept H0. Now, the above really comes from taking the log of the likelihood ratio and lumping theta and sigma into the yet undetermined threshold. And as indicated, it's convenient to divide by n for normalization. All the Z bars are in the same range regardless of the number of samples n. The Z bar is called in this case the test statistic, the function of the observations used in the test. So what we do is, in order to carry out the test, we don't need the individual observations one at a time or the whole collection anymore. It's enough to have their sum with appropriate normalization for convenience. Now, the threshold lambda 1 will be obtained by noting that Z bar, this is the average, is Gaussian distributed. Its PDF has argument Z bar, its mean is 0, its variance is sigma square over n. And we are going to put a condition that the probability of declaring or accepting H1 prime when H0 is 2, that's a false acceptance of the alternate hypothesis or false alarm probability, which is the same as probability of Z bar exceeding the threshold lambda 1 given H0, is 1 minus the integral from minus infinity to lambda 1. It is the integral from lambda 1 to plus infinity, but we more conveniently write it because these things are tabulated in the fashion. That's a cumulative distribution, Gaussian distribution here. So this is the integral of a Gaussian with mean 0 and variance sigma square over n, and this has to be alpha. Now, we can look at another version of this problem where instead of having a one-sided alternate hypothesis, H0 is theta 0, H1 theta positive, we can say H0 is 0, but the alternate hypothesis, H1, says plain non-zero, which means it can be either positive or negative as long as it is non-zero. So we are really interested in a situation, and this is in parameter estimation. Do we have a parameter which is 0, which means there is no parameter, or there is a non-zero parameter? These are now the more realistic, closer to real engineering life type of problems. So our H1 is theta is non-zero. Now, the test statistic in this case is almost the same as before, except that we have to use the magnitude of z bar if this magnitude of z bar, which is the sample average of the observations, exceeds the threshold lambda, still to be determined. We accept H1, that the parameter is non-zero. If it's below lambda, namely it's close to 0, and that's the meaning of close enough that comes now into the picture, then we accept the null hypothesis. And we again obtain the threshold for this decision by putting the condition that the false alarm probability, namely accepting H1 when H0 is 2, which is the probability that our test statistic, the magnitude of z bar, exceeds this number lambda under H0, which is 1 minus the integer z magnitude exceeding lambda. Really, you cut out the two tails. So this is the probability where you would have a false alarm. This is given by 1 minus integral from minus lambda plus to plus lambda of the Gaussian density under hypothesis H0. So the argument is z bar, the mean is 0, the variance is sigma square over n. This has to be alpha. So the sum of the two tails probabilities would be alpha. Typically each tail will be taken as alpha over 2 because of symmetry in this case. So lambda is such that the acceptance region for H0, which will be the interval minus lambda to plus lambda, contains 1 minus alpha probability mass of the PDF under H0. Cut out the two tails, you're left with the mid part, and that will be 1 minus alpha. Again, think of it like, say, 95% of the probability mass is there. Now, if alpha is 5%, 0.05, one obtains from the tables of the normal distribution, again, we'll see this in a few minutes, lambda is 1.96 times the standard deviation. Variance was sigma square over n, the standard deviation is sigma over root n, so for each value n we have a different threshold, obviously. Now, as before, the power of the test will depend on the specific value of theta under the alternate hypothesis. The farther away from 0 the non-zero value of theta, the value under H1, which we don't know, the more powerful it is. We'll still have the same false alarm probability, but the detection will occur much more often, because if it's there, obviously you are far from 0 and the noise will create less confusion. And we have in this figure the acceptance region. This is the PZ bar H0. Here is to the left of minus lambda 2.5%, to the right of plus lambda 2.5%, in between is 95%. So we reject H0 if the sample average of our observations is in this area or in this area. And the total probability for this happening when the true average is 0 is 5% exactly. So we have the acceptance region for H0. We have the two-sided 95% probability region. That's the interval minus lambda plus lambda. And the shaded areas represent the tails, which we cut out with total probability of 5%. In this region, we reject H0, therefore we accept H1. With small probability, it will be an incorrect acceptance, will be a false alarm. Now, the difference between the sample mean z bar and the true mean theta, whatever its value is z bar minus theta is distributed Gaussian with mean 0 and variance sigma square over n. That's because under H1, if z bar is distributed with PDF as we have indicated before, argument will be z bar, mean theta, variance sigma square over n. We can move the theta to this side and then it becomes a zero mean Gaussian. So based on this, you see that everything depends on the difference between z bar and theta, and this holds for any value of theta, even for 0, that's true. You can say that the true mean lies within the interval z bar minus lambda to z bar plus lambda with confidence 1 minus alpha. Now, theta is really not a random variable, so you cannot make a probabilistic statement about theta, but you have what is called a confidence region of theta, because z bar will be around theta with some probability. Therefore, theta will be around z bar, naming the z bar minus lambda, z bar plus lambda, but you don't say probability, you say confidence. Therefore, the estimate of a parameter which might be 0 will be accepted as significant, statistically significant, at a level of 5% of the null hypothesis. We mean by this that we are willing to commit a 5% error probability of false acceptance of H1 if theta hat, which is the z bar, divided by sigma theta hat, that's the variance of z bar, exceeds 1.96. It's really 2 standard deviations of its estimation accuracy away from 0. And we determined the threshold under the normal assumption and the fact that sigma theta hat is the same as sigma z bar, because really z bar is our best estimate for the parameter theta. The question is, should we take it as is or should we throw it out, saying it's too small, it's insignificant, we don't believe in it, we still accept that the true value is 0, and the fact that z bar came out non-zero is just due to the noise. In principle, z bar will always be non-zero, even if theta is 0. Just take a bunch of random variables with 0 mean, add them up, take their average. You'll never end up with a value 0 exactly. You usually end up with a small number. So the small number is measured by theta hat or z bar. If it's below 2 standard deviations, and this is the standard deviation of theta hat or z bar sigma over root n, also called the standard error. This is the standard deviation of the estimate or the standard error. Then we say, forget it, the true value is 0, I don't believe in it. If it's away from it, we call it if the value z bar is sufficiently far away, as this equation 17 says, from 0, then we accept it as statistically significant. Then we have a parameter that we estimated. So what we have now is a definition of the estimation error that can be stated as theta minus theta hat. And we can do a little bit of manipulations of probability density functions that show us the power of these representations as follows. The PDF of theta hat, which is an estimate now, given theta, is Gaussian. In our case, we have shown argument is theta hat because there's a PDF of theta hat. The mean is theta, and the variance is sigma theta hat squared. So some variance here. Right now, it doesn't matter what. However, the special form of the Gaussian really has in the exponent theta hat minus theta over 2 sigma squared. So I can say that my variable is theta hat minus theta, and my mean is 0. So that is allowed by the special form of the exponent in the Gaussian density. But this is exactly theta tilde. That's the estimation error. So this can be said that the P of theta hat given theta is the same as the Gaussian of theta tilde, the estimation error, which is really P of theta tilde. So what we have here, now also we can redo the notation, rewrite it, instead of sigma theta hat squared, a sigma theta tilde squared. So this is the variance of the estimation error. So what we have is the standard deviation of the estimate about the two means sigma theta hat is the same as sigma theta tilde, which is the standard deviation of the estimation error, which is zero mean. Sigma theta hat is the same as sigma theta tilde. So all these are allowed thanks to the special form of the Gaussian density. Let's take an example. We estimate a parameter theta from n measurements. Each has an additive error with standard deviation 10. Assume that we had n equal 10 such measurements and we obtained an estimate of theta hat equal 2. What is the significance of this? Shall we accept that this is zero value or the value, the best guess is 2? The significant statistic at a level of 5% in this case will be theta hat divided by sigma theta hat, which is the estimate that we got, that's in magnitude 2, divided by sigma over root n, that's 10 over root 10, 2 divided by this is 0.63. This is significantly smaller than 1.96, which I call it in general 2. So that's less than 2 sigma away from 0. In other words, based on these n equal 10 measurements, the estimate is clearly not statistically significant. Therefore, in such a case, we'll say, based on our data, we can assume the parameter is 0, which means we accept the null hypothesis. This threshold that we use is for the 5% level of significance. Again, that's 5% probability that the estimate is due to noise only, or 95% confidence that it is non-zero. Now, assume next that the observations are repeated until we have 100 measurements, and assume the estimate is still theta hat equal 2. What is the significant statistic in this case? Theta hat, that's 2, sigma is 10, n is 100, root n is 10, so it's really 2. Now we are just above the threshold, namely based on 100 measurements. If this is my estimate, I end up with a statistically significant estimate, even though only marginally. So, and the reason is, it is very unlikely that from 100 measurements, if the thing is 0, I will get 2. But it's not unlikely at all that I will end up with a 2 value if I take only 10 measurements. So I increase my confidence, and now the same value is statistically significant. And that's because of the number of measurements. Now, on several occasions, we already use tables really of the Gaussian distribution, not of the chi-square, but we'll use both later. And we'll see in a moment, points x on the chi-square distribution for a given upper tail probability. Remember, this is really the complementary distribution. Q is the tail. Typically, the cumulative distribution is P of y less or equal to x. You take the complementary event, and that's called the tail. If y is chi-square distributed with so-called n degrees of freedom, and we will write this as chi n squared 1 minus q. So on the cumulative distribution function, this would really correspond. The 5% tail is a 95% point on the cumulative distribution function. So this is the percentile point. If you multiply by 100 times 1 minus q, you get the percentile point. So the probability mass to the left of this point is 1 minus q, to the right, and this is the tail or the right tail, it is q. The 95% probability region for a chi-square with 2 degrees of freedom variable can be taken as one-sided by cutting the 5% upper tail, and then you end up by looking at the table from 0 to about 6, or two-sided. You cut off 2.5% from the left tail, 2.5% from the right tail. So this is chi-square at 0.025 and at 0.975. This is 0.05, 738. Now, for 100 degrees of freedom chi-square, you cut off again 2.5% from the left, 2.5% from the right, you end up with 74, 130. You can see that the chi-square with 100 degrees of freedom, which has a mean of exactly 100, because it's the sum of 100 squares of Gaussians with mean 0 and variance 1. So the expected value is 100. It is still not symmetric. The upper tail is a little bit heavier than the lower tail. It's skewed. The last line in the table shows the points on a standard, namely 0 mean unity variance, normal or Gaussian. So Y is distributed with mean 0, variance 1, and Q is the tail. And the script G, 1 minus Q, is the point that we have. This is the cumulative distribution at point 1 minus Q, or tail Q. You can see that for the 2 degrees of freedom, if you have left is 0.05, 2% cut on the left, 2.5% on the left, 2.5% on the right is 7.38. If you cut 5% on the right, it's 5.99, the upper limit, and then the 95% starts from 0 to 5.99. And so on for other numbers of degrees of freedom. For the Gaussian, if you want the 2.5% on the right and on the left, it's minus 1.96 to plus 1.96. So this is 99%, 97.5%, 2.5% cut on the right. This is 1% cut on the right. You can see 1%, and this is 0.5% and 10 to the minus 3. So the Gaussian at 3 sigma has a 1/10 of 1% tail left on the right. So with the notation that we introduced, the 95% two-sided probability region for a 0, 1, a standard Gaussian, would be, this is the notation based on the cumulative distribution function. That's 2.5% from the left, 97.5% from the left, or 2.5% right tail is approximately minus 2 to plus 2. The one-sided 95% for a standard Gaussian, on the left starts at minus infinity, on the right ends at 95 percentile, so at 1.64.